Everyone, welcome to another lecture video for Unit 6 on energy resources. Today we're going to talk about nuclear energy, what it is, what are the pros and cons, and what role it's going to play in our future. So nuclear energy relies on a chemical phenomenon called fission. Fission is just the breaking up of an atom, or the nucleus of an atom. It is what drives the energy behind an atomic bomb. So in a nuclear reactor, basically what they're doing is they're firing neutrons at the nucleus of a large atom like uranium or plutonium, and that large nucleus splits up into smaller nucleuses. Other neutrons fire off, and it causes this chain reaction, and that releases radiation. That's what this movement of these neutrons is, and it releases a lot of heat energy, as well at the same time. So radiation, which is the flow of these subatomic particles, can take the form of X-rays, infrared, ultraviolet. We've talked about all those before, but also things like microwaves, radio waves, and gamma rays. Radiation can be harmful. X-rays and gamma rays can cause radiation sickness, can lead to skin damage, organ failure, cancer, and death if you've been exposed prolonged. Quick exposure, like when you're getting an X-ray, will not do a ton of harm, but if you're exposed chronically, that can do a lot of damage. And you can be exposed to it directly, you can ingest it, it can become airborne or waterborne. So there are lots of different ways for it to impact a variety of ecosystems. But it's not like it's leaking out of nearby power plants. So this fission reaction is harnessed within nuclear reactors, and nuclear reactors work somewhat similarly to coal or gas or oil power plants. So inside the nuclear reactor, we've got this containment structure, and inside there is a reactor. And within that reactor are these things called control rods, which I'll show you a picture of in a second, and they host the uranium fuel source. And the fission reaction is happening within that reactor vessel, and that's generating a lot of heat. And that heat, much like in a coal power plant, is used to turn water into steam. That steam flows through a tube, turns a turbine, which turns a generator, generating electricity. That steam will then condense. It'll use the plant will pump in cold water from a nearby river or something like that to condense the steam back into water, which then flows back through. These fuel rods here that are generating the heat are rods that contain little uranium pellets, about that large. And they have a ton of pellets within them and are generating a lot of electricity. Some of the rods that are in this structure here, you can see all these individual rods in the fuel assembly. Some of these rods aren't fuel rods, they're what we call control rods. They're empty and they help absorb some excess neutrons and help the fission reaction from spiraling out of control and leading to a meltdown. So they help control the reaction, which is why they're called control rods. Nuclear energy has a lot of advantages. First of all, it has very little carbon footprint. The only carbon footprint is from mining the uranium and building the plant itself. But if you look at this graph, we've got different energy resources and amount of CO2 released per unit energy on the y-axis. You can see that nuclear energy produces very little CO2, which is great. It's also a very large-scale production. It produces a lot of energy. The energy is very consistent. It doesn't fluctuate over the course of a day like with something like solar or wind. It doesn't fluctuate in terms of energy demand either because the fuel pellets are so densely packed with energy. It has a pretty high energy return on investment. These pellets, a typical pellet weighs about 7 grams, can generate as much energy as 3.5 barrels of oil, 17,000 cubic feet of natural gas, or 1,780 pounds of coal. So there's a lot of energy within one of these pellets, and you've got a lot of pellets in each rod and a lot of rods in each reactor. There are some downsides of nuclear energy, however. You may be familiar with some of them not so much. I'll talk about thermal pollution in a little bit more detail soon, but the coolant liquid that is used to condense the steam back into water that is pulled from nearby aquatic ecosystems, that water is absorbing the heat from the steam, and as it gets ejected back into aquatic ecosystems, you've got warm water that can reduce the dissolved oxygen in these ecosystems. Nuclear reactors can spiral out of control and have what's called a meltdown. The plant loses power, the coolant will stop flowing, and it can cause the fission reaction to go out of control. Uranium is a non-renewable resource, and it has to be mined. And in that mining process, you can release greenhouse gases and also other environmental concerns and human health concerns related to radiation poisoning and issues of environmental justice. Radioactive waste lasts a long time. Once the fuel rods have been used up and they can't generate electricity anymore, they need to be disposed of, and they need to be contained for a very long period of time. Sometimes, though, although they can't generate electricity, they can still be used to generate nuclear weapons. And lastly, these nuclear power plants are very expensive and they take a long time to build, so the upfront cost is very high. Let's break some of these down. First of all, thermal pollution. This is the same image I was showing before. We've got the steam that is circulating through. The steam is condensed back into water by coolant fluid that is brought in from nearby aquatic ecosystems. And when this is brought in from nearby aquatic ecosystems, it's absorbing that energy from the steam, so it's leaving and going back to the aquatic ecosystems much warmer than it was initially. So you've got a bunch of water, warm water, being ejected into these aquatic ecosystems, and it's raising the temperature of that the water that these organisms are living in. And warm water doesn't hold gas as well as cool water does. Think of like a cool soda versus a warm soda. Warm soda is very flat, doesn't hold the CO2 bubbles very well, and that's true of oxygen as well. So you've got issues where not only are you changing the range of ecological tolerance, or not the range of ecological tolerance, but you might be increasing the temperature of the water. You're also decreasing the amount of dissolved oxygen available in the water for organisms to breathe, because warm water holds gas less efficiently. Thankfully, many power plants use these things called cooling towers. You might think that this is the nuclear reactor itself. A lot of people think that. It's not. It's actually a tower used to help cool off the liquid. So this circulating water will often pass through a cooling tower to help basically sweat off a lot of that heat. It's got like fans and stuff in there, so that way to reduce thermal pollution in nearby aquatic ecosystems. So this stuff here is just steam. It's not like smoke or smog or anything like that. It's just steam. Another downside is the meltdown. If the fuel rods become too hot, they can melt down. Inside the reactor vessel, we've got fuel rods and control rods, and they've got a coolant fluid as well that helps to keep things cool and from overheating. If the pump that pumps in that coolant water fails due to a power outage, which is what happened in Chernobyl, basically, that coolant will evaporate and the fuel rods will overheat, and it can lead to a meltdown or a massive release of radioactivity. There are three famous nuclear meltdowns: Chernobyl, 3 Mile Island, and Fukushima. So let's talk about them and see if we can figure out which one was worse. 3 Mile Island was located in Pennsylvania in 1979. The cooling water valve was closed, so all of that led to a partial meltdown in the core. 200,000 people were evacuated from the area. There's speculation that infant mortality rates and cancer rates have increased in the area afterwards, but it was a relatively low impact. It wasn't like an explosion or anything like that. Chernobyl, which is probably the most famous one, here's a picture of the reactor core. You can see a massive explosion there. It was in 1986. During a test, they disconnected the cooling system on accident, so a test turned into a real-world scenario. So the plant overheated, a massive explosion and fire. 31 people died immediately. Many more died later due to radiation exposure and the fact that the Russian government was trying to cover it up at the time. Cancer deaths increased substantially. The winds blew radiation all over the area, contaminating crops and milk, and the area has been uninhabitable ever since. They are working on a confinement project that was just completed a couple years ago. They basically built this giant structure that they rolled over on top of the facility here. This is the nuclear plant, and this is the structure they built. They're expected to clean up the nuclear waste by 2065, and that whole area is pretty much uninhabitable. And the most recent one is Fukushima Daiichi in Japan in 2011. There was a massive earthquake, which also triggered a tsunami, led to major flooding, and it disrupted the generators in the plant that were helping to keep the coolant water flowing. So it led to interruption of the power supply, massive explosion, hydrogen gas explosions, and radioactive gases were released. Many of the reactors were destroyed, 100,000 people evacuated, and the water and the aquatic ecosystems nearby were contaminated with radioactive waste. And Japan has a pretty big fishing industry, so that was not so great for them. You could see some of the area nearby has been abandoned so long that grass has started to overtake the cars that were left behind. Something to keep in mind is that all of these plants, 3 Mile Island, Fukushima, and Chernobyl, were built in the 60s or 70s. So their structure and their plans are kind of outdated. And that's something to keep in mind if you compare them to more recent recent power plants that are much more modern. A lot of people have this existential fear about nuclear power plants because of those 3 disasters, but it's a much lower risk than many people think. So here's a handy chart. If you can fill this out, you're in good shape for comfort level with these three nuclear disasters. Okay, and the big one that we're going to spend a while talking about is nuclear waste. Nuclear waste is a big challenge because there's really no way to dispose of it safely. It releases radioactivity, which is dangerous, as I already talked about, and the storage of this waste can outlast recorded history because it stays radioactive for a very long time. The rate at which it decays can be very slow. The current methods of storage have a maximum of about 100 years in terms of storing this stuff, but it needs a lot longer storage time than that. There are 3 different types of waste. There's high-level waste, which are used fuel rods, low-level waste, which are things like contaminated gloves and clothing and tools, and then there are mine tailings from uranium mines, which can have radioactive waste like dust particles and stuff. There are about 90,000 tons of high-level waste in the United States. That's a lot of waste. There are some misconceptions. I find students often think that nuclear waste is like this green ooze that leaks out of power plants and makes you a Teenage Mutant Ninja Turtle or something. That's not the case, right? These nuclear waste are spent fuel rods. So the rods that have the uranium pellets in them, after a while they can no longer be used to generate electricity but are still radioactive. They're not a ooze. They don't leak outside of the power plants. They're oftentimes stored in containment pools on site because the water shields the radiation. And sometimes these pools start to fill up though, so nuclear power plants have started storing them in lead-lined dry casks on land. And if you take a look, and if you take a look at this, they're lined with lead to help protect the outside from radiation leaking out. And there's a third option besides storing it in pools or in lead-lined casks is to store it underground in deep geological disposal. This is probably the best option, safest option for large, long-term storage of nuclear waste, but no country in the world has established a site for this yet because there's a lot of controversy about where you're going to put it. If you take a look at a map of nuclear storage sites all around the country, you could see that there are a few sites in Connecticut and New York where we are, and there's also this big site here called Yucca Mountain. Yucca Mountain was the proposed deep geological disposal site for the United States. It was proposed in 1982. It's in Nevada. And it's supposed to be a repository for the whole country for all of our nuclear waste, storing high-level waste, all of it or most of it in one place. It was near many of the nuclear test sites that were done in the 40s and 50s when we were testing the atomic bombs. And it was proposed in 1987. It was approved in 2002, but it has been started, but it has never been used, and it has never really been fully developed. Probably won't be for a lot of reasons. First of all, statewide opposition. Most people living in Nevada don't want it built there, and why would you blame them? I mean, who wants a nuclear test facility stored in their state? Especially because Nevada doesn't have any nuclear power plants. It's also built on and near indigenous land, and there's a significant lack of funding. So there are a number of issues around that. And on the point of indigenous land, these sisters, Mary and Carrie Dan, from the Western Shoshone tribe, Carrie actually just very recently passed away in early 2021, were ranchers, activists, and indigenous leaders in Nevada. They opposed many uranium mining projects, and they also were stark opponents of the Yucca Mountain, helped to postpone the development of that facility because it was being built on or near indigenous lands. And they also helped advocate for relief for many of the victims of the weapons testing that was being done in Nevada, testing atomic weapons. There are many cases of indigenous peoples living in that area who have suffered because radiation sickness because of the weapons testing. So really two cool women who fought for environmental justice and found a lot of success in doing so. They devoted their whole lives to it, and pretty famous within the environmental justice community. If we look at issues related to nuclear waste and environmental justice, we see them both in Australia and the United States and related to indigenous land, because in those areas there are fewer environmental restrictions on indigenous land because there are fewer protections afforded. In these lands, both in the U.S. and Australia, we saw atomic bomb testing being done on indigenous lands, which I mentioned has had negative impacts on the nearby population. There are uranium mines being built on indigenous lands, which can expose the communities to pollution from the toxic tailings. Also, the storage of nuclear waste on indigenous lands. Oftentimes the government is sort of bribing or trying to pay off these communities to store nuclear waste on their sacred land, and that can contaminate the soil, it can contaminate groundwater. 30% of Navajo people in the United States lack access to uncontaminated drinking water. And it can also lead to higher rates of cancer, death, and disease. There's actually a disease named after the Navajo people because it's so prevalent within their community called Navajo neuropathy as a result of exposure to uranium from uranium mines and storage of nuclear waste. Very high rates of Navajo neuropathy amongst Navajo women and babies in the United States. And if this is being done on their historical, cultural, and spiritual sites, so even that on its own is an argument against this whole developing of mines and storing waste, etc. Not to mention testing atomic bombs on their land, which is just crazy. If we look, it's not totally surprising. If we look at the uranium resources in the United States, we see a lot of them are located out west on these across various different states. And if we look at uranium resources in indigenous lands are these marked in purple, and uranium refining and processing plants are these little purple U's here. So you can see that there is a lot of overlap between indigenous land in purple and uranium resources. And you can see that there are processing plants built near or on indigenous land, and so they're going to want to dispose the waste nearby as well. So it's not surprising, but it is extremely disappointing and saddening. Okay, so one of the reasons that we keep talking about nuclear waste and why it's so dangerous and so bad, and I mentioned that it lasts a really long time. Right, so this process of radiation being released through fission can continue for a very, very long time, and it can stay radioactive throughout that time, and that's something called a half-life. So the amount of time that it takes for a sample to radioactively decay to half of its original potential is called a half-life. So, for example, sodium 24, the isotope sodium, will degrade at a rate of half of the sample will degrade every 15 hours. Carbon-14 will degrade every 5,730 years. Half of potassium-40 will take about 1.26 billion years. So you could see uranium-235, which is very commonly used in power plants, nuclear power plants, has a half-life of 704 million years. So in order for this nuclear waste to decay to a point to where it's safe, we're going to need a lot of time, right? Hundreds of millions, if not billions of years. Half-life can be used to calculate the rate of decay and the radioactive level at specific points in time. We're going to do a lot of practice with these types of problems, and we'll do a lab on it as well. When doing these types of math problems, you're going to probably come across either Curies or Becquerels, I don't know. I stopped taking French in high school, but they're both units of half-life decay. So let's do some practice. See if you can figure this out. So a sample has a radioactivity level of 100 Curies and a half-life of 50 years. What will the radioactivity be in 200 years? So let's walk through this together. We'll do 3 different approaches to this problem. First approach. Well, if 50 years is one half-life, So after 50 years, we'll be down to 50 curies, because 100 divided by 2 is 50. After another 50, we'll be at a quarter of the initial level, which is 25 curies. After another 50, we'll be at an eighth, which is 12.5 curies. And after another 50, we'll be at 1/16th, which is 6.25 curies. 50 plus 50 plus 50 is 200. 200 years. After 200 years, we'll be at 6.25 curies, right? The way I like to do it, the way I like to solve most math problems is by drawing a picture. So we start with 100 curies. And every half-life is 50 years. So 50 years go by, and it gets cut in half to 50 curies. Another 50 years goes by, it gets cut in half to 25. Another 50 years, it gets cut in half to 12.5. Another 50 years gets cut to 6.25. So we've had 4 half-lives go by. 4 half-lives, each half-life is 50 years. 4 times 50 is 200. That's the amount of years the problem is asking for. A third approach, there isn't actually a formula you can use to calculate half-life. You don't have to do this way, though. 200 divided by 5 gives us 4 half-lives. 4 half-lives will go by, so a half to the 4th power is 1/16. So 1/16 times the initial amount of 100 gives us 6.25. 3 different approaches to the same problem. You can do whatever one makes the most sense to you. I don't care. Give this problem a shot. If a material has a radioactivity level of 500 curies and a half-life of 30 years, what will the radioactivity level be in 150 years? Give that a shot. Okay, let's take a look. So we start with, if we do it this way, over 150 years, if each half-life is 30 years, that means 5 half-lives have gone by. So let's cut this in half 5 times. Or a half to the 5th is 1/32. Multiply 500 by 1/32, and you get 15.625 curies as the answer. That's how much radioactivity will be left after 150 years. Okay, so considering all the pros, the cons, the environmental justice, the half-life, there's a lot to take in about nuclear energy. Where is it today? There are about 440 nuclear reactors worldwide that provide about 10% of global electricity needs. In the United States, nuclear plants make up about 20% of our electricity needs. There are 95 reactors in the U.S., but only 1 has been built since 2000. So the rate of the building has gone down significantly. And most reactors are built to last about 35 years. So a lot of these might be starting to close down soon. That being said, in 2019, of the top 10 U.S. power plants by electricity generation, 9 out of 10 were nuclear power plants. So 9 of the 10 most productive power plants in the United States are nuclear power plants. If we look at the location of those plants, you can see they're scattered all across the country, quite a few in the Northeast. And if we look at nuclear power plants, all nuclear power plants, we can see a lot of them mostly located east of the Mississippi River. Looking ahead, Bill Gates has been working with this company called TerraPower, which is a nuclear innovation company, to develop a new type of nuclear reactor called a traveling wave reactor. It's highly efficient. It actually uses nuclear waste as its fuel, so it's tackling 2 problems at the same time. It's generating electricity, but it's also reducing the amount of nuclear waste produced by actually using it. And 8 metric tons of waste could provide about 2.5 million homes with electricity for a whole year. So it's extremely efficient and might make a big difference in the as we go forward, because the big question for you to think about as we move forward in this unit is, what role will nuclear energy play in addressing climate change in regards to energy usage? So I'll leave that question with you. Keep that in the back of your mind, and we'll talk about it next class. Thanks for tuning in.